product at Risk Zero. We're a ZK company. We built the first general purpose ZK VM based on RISC-V. If everybody saw Justin's tweets yesterday, or excuse me, talk yesterday, or at least the tweets, we were the first RISC-V ZK VM, and one of the ones he mentioned on his slide about how he hopes to see these ZK VMs integrated into the Ethereum layer 1. A little bit about me. Been around crypto since late 2014. It's been a long time. I look a lot older now than I did back then, and just got so excited about the potential for financial and digital sovereignty that learned to code in 2017, and worked in various PM roles at SaaS companies. Finally made it to work in ZK and crypto in 2021. Worked for O1 Labs, which is the labs code behind Mina Protocol. Just personal background, I'm a dad, father of 4, really love what we do in this space, trying to create a better future for our kids, a better future for the next generation, more free, more digitally sovereign, and so, yeah, just love what we do. So that's a little bit about me. Cool, I wanna kind of form this hypothesis, which is that we're heading into a 5th generation, not just of blockchains, but blockchains coupled to verifiable protocols. And hope to sort of form that hypothesis, talk a little bit about what that means for bridging and interoperability as well. But first of all, I think we have to recap. Why is it that blockchains matter? Blockchains provide this really important characteristic. They enable trust minimized coordination for anyone connected to the internet, really. And how they do that is through a characteristic we call verifiability, right? A blockchain only matters to the extent that you can traverse its history, ensure that the ledger is accurate, you can't do double spends, etc. And the way we get that characteristic of verifiability today is through consensus. That's important to remember. So how do we get this characteristic of, if I go back here, coordination, trust minimized coordination? How do we get that? We get it through, like I mentioned, this characteristic of verifiability. So verifiability, the fact of being true or correct. If a blockchain was not verifiable, it wouldn't matter, right? A SQL database is not inherently verifiable. You don't know if the information in it is accurate or true. And so this is a really key characteristic to all of the systems that we build on chain. Cool. Just running through the quick history of blockchains and sort of the evolution. First generation, oh man, these clickers going crazy. First generation of blockchains we had, this is, by the way, borrowed from an A16Z article way back in 2018. Made a couple modifications to it. But they called it the calculator era, was the first generation of blockchains. I'd call it the era of digital money. We had blockchains like Bitcoin, which did payments only, had very limited composability and functionality. Come 2016 and Ethereum, we had what they described as the mainframe area, or I would call this notion of programmable money today, where we first had Turing-complete, programmability over digital currencies. The capabilities of blockchains were extended beyond payments to verifiable, programmable systems. Ever since then, I'd say we've been, working within this third paradigm. There was like a number of chains where I was just like, you could name names, right? Back in 2017, 2018, and since then, that we're just all about making programmable money go fast. We could call that the scalability era. And then really, right now, we're in this modular era, which we're breaking apart blockchains and into their composable pieces. And I say composable quite lightly because, as we know, we've created quite a problem for ourselves. In the name of scaling, we've broken apart these systems and made them highly interoperable. And that's why the work that Union and the technology we're building are really integral to help build this 5th generation of composable yet scalable blockchain systems. All right, so that's the brief history. Let's see if I can get to the next slide. I don't think my clicker's working. Thank you. Cool, and so really, if I describe this trade-off space we've been in for blockchain design, it kind of looks like this. You can, if you're Ethereum, you prioritize decentralization, right? So you have quite a bit lower hardware requirements. You really want to have more nodes in the ecosystem, really maximize for decentralization. If you're Solana or Sui, you're okay, increasing the requirements, having sort of less nodes because you're trying to go burr, right? You're just trying to go fast. And all of these blockchains, we've been focused in scaling sort of in one vector, which is throughput. How many transactions can we get through the system at one time? But there's this really important aspect of scaling I think that we often overlook, like the block size limit. And you can actually think of this as just the raw execution limit of a given chain. This is a really important characteristic we'll come back to. And then, so you can kind of pick like bigger blocks or smaller blocks. Ethereum has, I think arguably more execution that you can do in an individual block than a Solana does. And you can understand why, right? Solana wants to go really, really fast, 400 millisecond block times. You have to keep your execution limits quite small in order to do those round trips within the chain and sort of execute those transactions within the blockchain. And then this last one I'll mention is block frequency. So Ethereum's at a lovely 12.8 seconds on average. Sui and Solana, for example, are under a second. I think 400 and 600 milliseconds respectively. And so you can see that we've mostly been focused on scaling across these three parameters. And you can think of the combination of these factors as maximum execution throughput, or the maximum throughput. And in execution, just to sort of define that term, we're talking about the length of a program that you can run. Again, sending just like a small token transfer, not a lot of execution, but it's like sort of one aspect and one way in which you could use execution. You can imagine that if you could run AI inference, that would be a lot of execution would be required to do that if you could do it on a blockchain. But it's basically impossible to do if we focus on scaling only in this direction or across these dimensions. So really, I think we can demonstrate that the result of this sort of paradigm and the way we've been focused on scaling within blockchains is that consensus is a bottleneck. If you can't do AI inference via consensus because you're really in a race against the speed of light. I can show you another slide here in just a second about that. If we go back one, actually. No, I'm sorry, the flat one. Thank you. So yeah, what you really see here is when you add a node to Ethereum, does it go any faster? No, it doesn't. Actually, it goes slower, right? Because there's more communication bandwidth required to sort of reach that extra node, include them in consensus, et cetera. And so we're really stuck in this paradigm today where a blockchain is only as fast in terms of throughput and execution as the slowest node on the chain. If we go to the next one. And why is that? Why is that true? So, next one too. All right, so if you look, you can kind of look at the Ethereum node itself, or the implementation of the blockchain itself as an example. So what's happening in the node? We recently, right? We had the merge, so we merged, ETH1 into ETH2, excuse me. And as a result, there's two clients today, two primary clients within, or really exclusively two clients within the Ethereum implementation today. An execution client and a consensus client. And these two things are communicating amongst each other. And you can see they're doing this really important thing. They're also communicating via P2P network. And so you can see that consensus and execution are directly coupled. You have to verify the execution or the accuracy of transactions while also communicating amongst your peer nodes and coming to alignment or agreement via consensus on those truths. So if we go to the next one. And so you can imagine this is, this is the Ethereum network. There's all these nodes. We're looking to achieve 2/3 consensus, right, to advance the state of the block. And all of these transactions and the validity of these transactions have to be run by computers spread around the whole world. And so this is really a race against the speed of light. We can only make consensus so fast. And if we want to get to sort of limitless execution or break the block, if you will, we really need an alternative solution to sort of get out of this consensus-based bottleneck that's limiting execution. All right. And so how do you deal with this, right? How do you scale up execution? Today we've made, I think, a really serious set of compromises that we're starting to see the negative side effects of. The one way, if you imagine that previous slide with just the flat lines, right? If every blockchain is limited on its execution throughput, you can just create new blockchains, right? You can just make a new blockchain, and that actually increases the amount of execution, that's available in aggregate. The problem is we're taking a really serious trade-off there because now we've sort of fragmented liquidity. I think this is just a very simple visual, roughly proportionate to the amount of liquidity on these available chains. You kind of have Ethereum over here with some satellite, L2s and chains, and then, these disparate chains that just pop up and aren't necessarily interoperable. And so that's why the work that Union's doing in particular, and these bridging operators, and why ZK Tech and all these advancements are really critical. We have to solve this. I think this trade-off that we've taken, which is just let's make a bunch of chains so that we can fix the throughput issue, and now we have this broken and fragmented sort of paradigm. And so yeah, I would just call this, we'll resolve this here in the slides, but just making up this idea of the composability bilemma. We've really sort of thrown the lever all the way to the right and focused on throughput through additional chains without much thought about ensuring the composability of these systems. And just a quick note on composability. What made Ethereum really useful, right? The ability to compose smart contracts in the beginning. And by sort of fragmenting these systems, we've really limited that value proposition of Ethereum and other blockchains. All right, so how does ZK fit into this? So what's really interesting, if you don't know what a ZK VM is, I'll give you sort of a quick crash course. But you can actually look at like that Ethereum execution client, the part of the Ethereum node that's specifically executing the transactions, ensuring that they follow the rules of the network. Every blockchain, right, has an execution client or is doing some sort of execution within the node implementation. And you can look at that, and it's actually very similar to a new piece of technology that we and others are now building, we've built and others are now building alongside of us, called ZK VMs. And so if we look at the execution client, there's a couple things. We've got sort of two various forms of state. We have a transaction pool. We have some like historical execution state that we're storing. And then we also have the VM, right? We have some execution model, some state transition function there in the middle. This is like how we advance the state of this memory sort of held in the execution client. And not to be neglected, this diagram's from the Ethereum Foundation. If you look at the arrows at the top, this execution client takes in data from consensus, so like sort of like recent truths about the network and like applies those as a state transition. And then it also sends out, provides a response to the RPC. So it's doing this sort of networking, providing these inputs so that we can come back to some verifiable truth, right? Like we mentioned that in the beginning is it's communicating with the consensus client so that we can get to verifiable truth and sort of perform consensus. And the way it does that eventually is through a P2P network. So a ZKVM is actually quite similar. We've got sort of two notions of memory. We have something called user memory. This is where you load a program into the ZKVM that you want to prove, amongst other things. There's also some memory for things like system, paging, et cetera. And we also have a VM or a state transition function. In this case, our ZKVM targets a RISC compiler target called RV32IM or RISC-V32IM. And so it's very similar actually construction. The key difference here, the arrows at the top, there's no P2P networking here. This can be performed directly on an individual machine and inherits the characteristic of verifiability thanks to ZK. There's no P2P networking necessary, and there's no communication with the consensus client within a ZKVM, right? We inherently export directly from the ZKVM a verifiable proof through mathematical proofs or ZK proof systems. And so despite, we essentially eliminate the consensus component and still maintain the verifiability component. That's really the key takeaway here. All right, so what does this mean? Like, what can you actually do with this? How does this really apply to blockchains? I think there's a couple cool little examples that I've given. And so if we can look at, okay, so when I say execution, I'm really referring to, let's say in an EVM context, the actual sort of opcodes executed in a given transaction. I broke down sort of those opcodes into three categories here for an ERC20 transfer as an example. You can look at the opcodes in an ERC20 transfer, and roughly a little bit more than 1/3 of those opcodes are that execution. And by the way, this is in terms of gas. 1/3 of that gas is spent effectively on things that have to happen on the chain. So if you want to log an event, that needs to happen over the P2P network. You want to tell everybody something happened, right? If you need to update the state of a smart contract, like I think the opcode is an S store in Ethereum, it's 3,000 gas. You have to do that in the P2P network because you sort of need to check in, you need to do sequencing, and you need to update state. In a simple, one of the simplest types of transactions here, more than half of the execution is actually mathematical operations that could be moved off chain into a zero knowledge proof quite easily in a general purpose ZKVM. Now, if you're savvy, you might go, okay, this is only 41,000 gas. Isn't a proof a couple 100,000 gas to verify? Yes, that's true, but you can imagine if you wanted to do 100 ERC20 transfers, wouldn't it make sense to move that 23,000 gas roughly off chain for those 100? So that would be 2.3 million gas you could move off chain if you were trying to sort of do batch operations. And so if we look at a Uniswap XSwap, it becomes even more obvious that there's really significant amounts of execution happening on chain today that could just be moved off chain if we had usable ZK systems and sort of an abundant supply of provers. So like a Uniswap X transaction, almost 200,000 gas. is just generic compute that could be moved off-chain. The other sort of 1/3 is things that we would need to be able to do on-chain. So you imagine you're a big trader on Uniswap. You want to put in 100 transactions and sort of not pay individual gas costs. There's really a lot of opportunity to increase the throughput of the chain through ZK. And the way that it increases the throughput of the chain, right, is ZK generates a proof of this execution, and that execution might be, really, really long, like 1,000 transactions, and all the chain has to do is like quick verification because ZK proofs are inherently much easier to verify than they are to compute. And so last thing I'll mention here is I'm using on-chain examples, but you can actually think of what Union is doing with ZK technology as another example of this. It wouldn't make any sense at all to write a smart contract that proves consensus of another chain, right? That's just not a use case that's possible inside of a smart contract. And so there's whole new areas of compute that ZK enables. Now what Union is doing is you can write a circuit, or in the experimentation they're doing with us and the partnership they're doing with us, they're moving that into our ZK VM where they don't have to write a circuit. They can actually generate a mathematical proof of the consensus of another chain. So there are whole new use cases that would not be possible without ZK becoming very, very accessible. All right. So just kind of in summary, ZK scales execution via verifiable computation rather than consensus. I think that's like a really important component. We can kind of decouple consensus and execution. And we know that we sort of have this second compelling option outside of consensus to really add execution to existing or new blockchains. Next slide for me. Thank you. Yeah, but the last one said, and we don't have to go back to it, it said, but isn't proving expensive, right? ZK systems are relatively new. Provers can be quite difficult and expensive to operate. The technology's been difficult to work with. And so, lots of advancements have been necessary. And I think it's really easy. I'm very close to the problem, so I know how fast these things are moving. But to the general public, it's really difficult to see and observe how fast this technology is moving. So as an example, last year we released a library called Zeth, and it was the first Type 1 ZK EVM. So in zero knowledge, with complete code equivalency and of the Ethereum virtual machine, we're able to generate zero knowledge proofs with this library of a given Ethereum block. When we built that last year in August, it was the first one. So I think the quote from Vitalik was like, "Who the fuck is RISC Zero?" Because he was really excited when he saw it. And we just sort of popped up out of nowhere. But there was a problem. We did some math, like we could generate a proof of an individual block. We did some math on what it would cost to prove all of Ethereum mainnet, and the dollar amount was quite ridiculous. It was like $170 million a year is what we estimated it would cost to prove all of Ethereum mainnet. That was August of last year. So as a product manager, I'm kind of like, hey guys, this is really cool, but we have a problem, right? And we've been very focused on making this thing go burr ever since then. Really happy to share that since then, we've brought the cost of proving Ethereum mainnet in that same library Zeth down to under $500,000. So this is a zero knowledge proof of the execution of every single Ethereum block we can do today for under $500,000, which is incredible. I'll have a couple other numbers here to sort of put this into perspective. All right, so what does this mean? The average Ethereum block, this is like a sample of a bunch of Shanghai blocks. That's what the footnotes sort of say here. But the average, we sampled a few hundred blocks. The average fees in these blocks on Ethereum was about $1,700, $1,686. We can generate a zero knowledge proof of those blocks for well under $1. It's actually under, I think, 50 cents in many cases. And so you can see that the execution bottleneck has a real cost. There's an artificial scarcity for execution on blockchains, right? Like you have to keep the limit low so that you can't attack the network. And ZK completely uncaps that limit on execution and eliminates that scarcity. And so, yeah, I think that's a really nice example on the blocks. Here's another example. There's a DeFi project. You guys would all recognize the name, but we haven't made the announcement yet. They're using our ZK VM to do to basically move what they would want, smart contracts they would want to execute off-chain, but are just way too big and infeasible. They're using the ZK VM to execute those smart contracts off-chain. And so they wanted to be able to query the state of 400,000 smart contract accounts in a single proof or transaction. On Ethereum, that would be 40 full blocks of execution, right? I was very lazy with the math here. This is a best case scenario to fill up 30 blocks of execution. I didn't scale the base fee like EIP 1559 would require. I just assumed constant gas costs. So this is really best case that would cost, if you're lucky, $40,000 to do in execution. And they're able to do that in our ZK VM for around $20, including the cost of the proof and the verification of the proof. So really, we've gotten to the point where ZK execution is incredibly efficient, and it's only getting better. All right, cool. So we looked at sort of these, we had these previous bars before. If we layer ZK into them, is like, okay, ZK requires pretty significant hardware requirements. You typically need a GPU to get this type of performance, and so it's more dramatic than I'd say any of the rest of these blockchains. There is no limit on execution. I think that's really important. There's been key innovations. We were the first ones to build something called continuations, which essentially lets you prove a program in perpetuity. We can just sort of split your program into all these smaller proofs and just keep proving it as long as you want to. So we effectively have no limitation. We've completely removed the limitation on execution limits. And then you can imagine if you designed a blockchain that was sort of ZK-centric, I don't know, you have some similar block frequency. But the key thing here is that we have really uncapped execution limits via ZK, and this is going to dramatically transform the space. So if we look back, yeah. Oh, no, I'm sorry, forward, yeah. But that is sort of a false paradigm on that last slide. We don't need more blockchains, to be honest. There's plenty of like consensus-based networks. It's our personal view that it would be better to enhance existing blockchains with these capabilities rather than to build whole new blockchains. Why not build on the protocols we love? We don't need another layer one. Shoot, I don't know if, we don't need many more blockchains. That's certainly for sure. And so you can imagine that the beauty of ZK is you can actually take those capabilities and those benefits and layer them on to existing chains, with little to no modification in many cases. All right, and so what would that look like if we could combine the benefits of ZK and Solana, ZK and Ethereum? We enter this paradigm in which when you add ZK nodes to an existing network, the limits on execution increase, right? So you get to this paradigm where you're no longer bound by the performance of your slowest node. We can do a small verification on-chain via consensus of a really long computation. And so for every ZK node that starts working for Ethereum or working for Solana, actually increases the throughput through the compression of ZK, increases the throughput of that chain. And so, yeah, we're building a protocol to do this that basically gives existing blockchains this power, this incredible power of ZK. It's called Boundless. I'll tell you a little bit about it. So number one, Boundless is two things. It's a set of standards for basically enabling every chain the access, abundant and easy to use access for ZK. So it's a set of standards for ZK execution clients like our ZK VM, requesting proofs, matching proofs with provers, aggregating them, and settling them onto given blockchains. And then second, it's an off-chain network of massively parallelizable ZK supernodes. We built some really cool technology that lets you plug in hundreds of GPUs to generate proofs, these execution proofs. So we call Boundless the universal ZK protocol, sort of as a summary of those two characteristics. It's the first end-to-end protocol for enabling the power of ZK on every chain. Again, like sort of what Alia is doing and what Mina is doing, these are all cool things, but the reality is because of something called the succinctness characteristic of zero-knowledge cryptography. What that means is you can generate an arbitrarily long proof or run an arbitrarily long program, and it has a small constant cost of verification on chain. It enables us to give these superpowers, if you will, to every existing blockchain. And so what happens when you do this? When you create an abundant supply of zero-knowledge proofs at really low prices, and you make it really easy for developers and users to access this off-chain execution as an alternative to on-chain execution, we really lay the groundwork for three important things. Number one, this is a new scaling vector. We've been focused on sort of XY axis scaling. This is sort of a Z vector for scaling. It's not higher throughput, right? But it's not higher throughput in terms of transaction count. It's higher throughput in terms of execution. So we enable this really important new scaling vector. Number two, and this is why the work of Union and others is so critical, is we dramatically improve interoperability. So right now, chains basically can't talk to each other except through multi-sigs or sort of other trusted solutions. Because we now have this unbounded amount of compute where any computer in the world can now contribute to the execution of a blockchain, we can do incredible things like prove the consensus of other chains, prove all of the execution of other chains, and this makes them highly interoperable. So obviously this is central to the Ethereum roadmap, but we're really making this available to every single chain. The last one is we lay the groundwork for privacy protocols. Privacy hasn't worked for a number of reasons. To some extent, as consumers, we don't care about it, or we've demonstrated that we haven't cared about it. But once we have this sort of extensive network of proof aggregators, ZK provers, et cetera, it'll be very possible, and once ZK Lite clients are readily available and abundant, it'll be really possible to land zero-knowledge proofs on-chain at a fraction of the price today. And this will have dramatic implications on privacy and make it much more possible to build privacy applications on any chain. All right, so what's like stuff you could build with this? This is kind of I'll show a couple names of people who are building various things, but you can build, various L1 scaling solutions, privacy solutions. Obviously, validity rollups is one of the simplest use cases for ZK that everybody would understand. You can build interoperable DeFi protocols. There's a team called Mendy building cross-chain liquidity protocol on Linea. And through zero-knowledge proofs, they can actually prove that you deposited or have funds on an L2 that would typically not be interoperable. You can build ZK bridges. What Union is doing is so critical to fixing the fragmentation and the lack of composability across the space. And you can build L2 interoperability solutions. Honestly, the list goes on and on. This is a creative endeavor. Imagine that we as humans, right, the faster and faster computers get, we find a way to use that additional compute, right? Just look at, AI. Computers are thousands of times faster than they were 10 years ago, or, let's say 30 years ago. Yet we've found a way where there's just not enough, GPUs in the world to do all of the training that we want to do today. So we're a very creative species, and there's just tons of new use cases that will open up by completely unbounding compute on these blockchains. Where are we at in building this protocol? So in March, we sort of kicked off a design exploration. We built 3 prototypes, a layer 1, a layer 2, and a smart contract-based platform. We liked the layer 2 and the smart contract-based platform. Again, we really don't need new chains. New chains introduce their own interoperability concerns, and we want this protocol to be workable on every chain. So we've kind of built a hybrid on-chain, off-chain system. More on the specifics of that will come out in December. In May, we kicked off an implementation for a private DevNet, and in July, we ran that internal DevNet. So we were able to run sort of our first testnet where you can post a request for zero-knowledge proof, and a prover fulfills it and settles it to the destination chain that you specify. Took a bunch of notes from that, learned a ton, and kicked off some upgrades, and we launched those in a program we called the Collaborative Development Program. Roughly 20 teams, half of them developers, half of them provers, participated in a permission testnet where anybody could sort of make a request for a proof, and these provers on the other side would settle and handle these requests. That was on Sepolia if you want to go try to dig up some transactions. And then come December, we're running our first public testnet. We're calling it an appnet because initially it'll only be open to application developers. Come Q1 of next year, we plan to open it to third-party provers as well. But really want to focus on the application developer experience and polish that up with another round of testnets and iteration. And so yeah, if you're a builder and want to come, access unlimited compute at roughly 1,000x more efficient than on-chain, Ethereum L1 gas prices, let us know. And I think I have a slide for. Oh yeah, these are some of the teams that are building on and working with us. And so Union, I think there's a partnership announcement going out today or tomorrow. I don't know. But it's coming up very soon, doing amazing work with ZK, proofs of ZK Lite client proofs. There's a number of L2s, provers, DAO protocols, Bitcoin L2s, DeFi protocols, etc. And so yeah, this is actually growing quickly. This slide is quite out of date. There's a lot of other teams that are working with us now. If you want to sort of build within this ecosystem, there's a lot of really exciting stuff going on. I'd recommend getting into our developer Telegram. Again, there's no public documentation yet. We've, for competition reasons, sort of kept that close to our chest. But come December, we do plan to run this appnet. Everything will be open source, et cetera. So yeah, thanks for listening to me, everybody. Appreciate your time.